Lesson 93. In this lesson, we will be looking at Bayes' theorem, which can be applied to solving conditional probability when you get new information that affects the probability of an event occurring. So let's start by revisiting the conditional probability formula for probability of B given A. So we recognize that it's going to equal to the probability of B and A divided by probability of A, which is the condition or the restricted sample space here. Let's call this equation 1. I'm going to consider what if I reverse the position of A and B, meaning that I'm interested in the probability of A given B. We know that the change that we need to make would be mainly the denominator, because now our new restricted sample space is probability of B. Knowing that probability of A and B is equal to the probability of B and A, that means I can rearrange this equation and say that P of A and B is equal to P of B multiplied by P of A given B, okay? So if I substitute this equation 2 back into equation 1 in the numerator, notice what happens. If I don't know what P of B given A is, but if I'm given P of A given B, then I can easily calculate the other conditional probability relating events A and B. Let's take this one step further. Now I'm going to focus on the denominator, your restricted sample space P of A. What if a sample space includes, say, 3 mutually exclusive events? What if a sample space U includes 3 mutually exclusive events B1, B2, B3 as shown in the first diagram here? If these guys form a partition of the sample space, then the probability of getting B1 or B2 or B3, so here, here, and here, okay, can be found by simply adding P of B1 plus P of B2 plus dot 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 plus P of Bn up to n partitions, okay? Let's introduce another event A now. And suppose that this event A spans or overlaps all 3 partitions, B1, B2, B3, as shown on this diagram. Then how do I find the probability of A altogether? Well, I need to then consider P of A and B1, right, the intersection, plus P of A and B2 plus P of A and B3 to make up the entire region of A. Using that relationship that we have developed to link up intersections as well as conditional probability, then each individual intersection probability of A and B1 can be calculated by multiplying P of B1 times P of A given B1. And you can repeat for the other sections, okay? Why is this useful? Because now we have a generalized formula that we can use in the denominator of Bayes' theorem. If I need to break it down further, that P of A as a restricted sample space, I can use this particular line here to help me calculate my conditional probability. Okay. From your IB formula booklet, you're going to find 2 Bayes' theorem formula relating to 2 events or 2 partitions versus 3 partitions. So the top formula here relates to having 2 partitions, namely B and B prime, okay, in the universe. So whatever happens B doesn't happen in B prime. And if I'm interested in the occurrence of B in the event A, but A does overlap both sides of B and B prime, then you can use the top formula. Okay. The bottom formula deals with 3 partitions of your sample space. So you have, let's say, something like that. So this is B1, B2, and B3, and once again, event A overlaps all 3 of them. Then you can adjust your denominator using the relationship that we have found. Okay, and the top part is still your P of A and B, really. Okay. Now let us look at example 1. A manufacturer produces nails using 2 machines. Machine A produces 60% of the nails and 4% of those it makes are defective. Machine B produces 40% of the nails and 5% of those it makes are defective. Find the probability that a defective nail comes from machine A. Okay, I should continue to part B. But anyway, we can still draw a tree diagram to represent the situation. All right, so we know that there are 2 machines. So either machine A or machine B, or here I can also call it A prime. And then I can label the probabilities too. So 60% of the nails come from machine A. I can call this P of A. And then the other 40% of the nails come from A prime. Okay. Out of all the nails that are produced by machine A, 4% are defective. So let's call it defective and D prime for not defective. So I've got 4% here. How can I properly label this probability? I can certainly call it the probability of a defective nail, but not only that, knowing that, so given it came from machine A, okay? Which means that probability of not defective given it's coming from machine A would be the other 96%. Not bad. And then I also compare defective, non-defective nails here, and 5% from machine B are defective. So let's call this 0.05, 0.95 then. And here I can say this is D given A prime and P of D prime given A prime. Okay? So what are we interested in finding? We're interested in finding the probability of a defective nail which comes from machine A. So let's process this. A defective nail comes from machine A. So the subject here really is, we already know that we're looking amongst the defective nails, meaning that's our condition. I don't care about anything that is not defective, and it came from machine A. Okay? This is conditional probability, so we're looking for P of A and D, right, over P of D, which can be expanded into the denominator. At least let's see it for once. This is P of A multiplied by P of D given A, and then anything defective comes from P of A times P of D given A plus P of A prime times P of D given A prime, for us to account for all the defective nails. Okay, so don't forget that. I need a little bit of room here. So what have we got? We have 0.6 times 0.04 over 0.6 times 0.04 plus 0.4 times 0.05. Okay. Using my calculator, I have 6/11. Okay. So let me write a note on the side here. In this question, it is very specific that it's saying that I am looking amongst all the defective nails, right? So this is not the same as finding P of defective end from machine A. Because if I just talk about the end part, it takes away that the fact that we have actually reduced our sample space. Okay. Okay. Here is number 2. T-shirts were printed for 120 volunteers and 30 staff attending a robotics competition. 36 small, 58 medium, and 26 large size T-shirts were given to volunteers. 4 small, 17 medium, 9 large size T-shirts were given to staff. A. A volunteer lost his T-shirt. Find the probability that it is a medium T-shirt. So here we know that is a volunteer shirt. So right away that gives us the hint that it will be a condition here, right? Perhaps before that, let's list out using a tree diagram how many volunteer shirts versus non-volunteer shirts, and then the sizes, small, medium, and large. Okay, goes here. So there are 120 volunteers, but 30 staff. So I should have a total of 150 people. So 120 goes here, and then 30 out of 150. Okay, these are the P of V's, P of V prime. Amongst the 120 volunteer shirts, 36 are small, 120, and then 58 medium. Okay, and then 26 large. Okay, and then for the staff T-shirts, there are 4 small, and then 17 medium, and then 9 large, like that. Okay, so part A, we know that this is the volunteer shirt. Find the probability that this is medium. All right, so we need P of medium and volunteer over P of all the volunteer shirts. And to get the top part, I multiply 120 over 150 by medium is 58. 120. And then probability of volunteer, I know is 120 over 150. Okay, the first branch. So let's see. I can cancel the 120. So the numerator becomes 58 over 150. Denominator is 120 over 150. So that means I can further reduce. That's convenient. 58 over 120, both are even numbers. I can reduce. Okay. Part B. A small T-shirt was found in registration. Find the probability that it belongs to a staff. Okay. Does it sound different from the first part? A small T-shirt was found. So all I care about is now, well, amongst all the owners of these small T-shirts, right? So that means here the condition is small size. And the probability for V prime staff. Okay. How does this look? This is P of V prime times P of S given V prime over, I have P of volunteer. So now all the small shirts need to be counted for. So S V plus P of V prime, P of small non-volunteers. Okay, so V prime is 30 over 150. S given V prime is 4 out of 30. And then P of V times small size, 36 out of 120. And then the same thing as the numerator. Okay, so simplifying and then reducing, most likely, it should work out to 1/10. How are we doing so far? I hope it's not too bad. Like the formula itself does look a little complicated, but when you use a tree diagram to organize your information, it's actually not that bad, right? Because you know that you have to account for all the outcomes in the experiment that sums up the restricted sample space. Okay, so let's do one more. Example 3. Allie has 2 toy bins. In bin A, there are 5 Pokemon toys and 6 Disney toys, while in bin B, there are 3 Pokemon toys and 4 Disney toys. Her brother moved 2 toys from bin A to bin B, and then 1 toy is taken from bin B. Ooh. So let's list out what they have. Bin A starts with 5 Pokemon and 6 Disney. Bin B, 3 Pokemon, 4 Disney. Find the probability that a Disney toy is drawn from the second bin, B. We know that the probability of getting a Disney toy when Allie draws it from a bin depends on how many Disney toys got moved from bin A to bin B, correct? Which technically means that we have to consider all the scenarios that could happen, meaning that either out of the 2 toys that got moved, 2 are Disney, 1 is Disney, 1 is Pokemon, and also none of the Disney toys actually got moved. This will affect the number of Disney toys in the second bin because it may change from 4 to 5 to 6, okay? So let's write this down because number of Disney depend on which toys got moved from A to B. Okay? So let's find the collective probability. So we know that the partitions here is how many Disney toys actually got moved. Okay? So P of A1 times P of B given A1 plus P of A2 times P of B given A2 plus P of A3 times P of B given A3. Okay? So how do I figure out P of A1? When 2 Disney toys were moved from bin A to bin B. Well, there are 6 Disney toys. 2 were moved in this case. Out of how many toys in total? 11. Picking 2. So we need to count using combinatorics. Times the probability of B given A1 is 6 over 9. Okay? Because then you end up with 6 Disney toys, right? With the addition of 2 in bin B. Out of the 9 toys now you have. Plus, if you end up 1 Disney toy, so 6 choose 1, and then the other must be coming from the Pokemon, so 5 choose 1. Over 11 choose 2. And then now you multiply by, there are 5, so 1 additional Disney over the 9 toys that you have in total. Plus A3, you're moving none of the Disney, so only 5 choose 2 with the Pokemons. over 11 choose 2. And then now you still have 4 Disney toys over 9. Okay? So this is 2 over 11 plus 10 over 33 plus 8 over 99. And so 56 over 99 is the probability. Okay? Now, B. Given that a Disney toy was taken from bin B, find the probability that 2 Disney toys were moved from bin A. So we're really talking about scenario 1, A1. And given is a Disney, okay? Event B. So here we have probability of A1 times probability of B given A1 over a restricted sample space of P of B, and thank goodness we have found it in part A. We don't have to repeat that tedious calculations. So this case is scenario 1, the first term, okay, from part A, which is the 2 over 11 out of 56 over 99. Okay, so these numbers are from part A. Okay, simplifying this, I got 9 out of 28. Okay,